Hello students, welcome to the lecture series of Mechanical Properties of Fluids, Chapter 2 of Class 12th Maharashtra State Board. Okay, so let's start with the first topic of the chapter, which is nothing but fluids. Now, if we go with the definition of fluids, it is as follows. Basically, fluids are nothing but substances that can flow. Therefore, we can easily say that liquid and gases are fluids. In this chapter, the type of fluids that we are going to concentrate on are nothing but ideal fluids. Now, how do we recognize ideal fluids? The answer for that is already on the screen. There are certain set of properties that the fluid must satisfy to be called as an ideal fluid. Now, I'll just read out the properties first. So, to be an ideal fluid, the fluid must be incompressible. It must have an irrotational flow. The fluid must be non-viscous, and the flow of the fluid must be steady. So these are the four properties that must be satisfied for a fluid to be called as an ideal fluid. Now let us understand what actually these properties mean in detail. Okay, so let's start with the first property, which was nothing but the fluid must be incompressible. So what is the meaning of this incompressible fluid? Now, incompressible fluid basically means its volume must not change on applying pressure. Therefore, volume must remain constant. Now, we know that density is mass over volume. Density is mass over volume. For a given amount of fluid, the mass is constant and volume is also now constant. Therefore, as whole, the density has to be constant. So when a fluid is incompressible, it basically means that its density should be constant. It should not vary. The density should not vary. Okay, let's move on to the next property, which is nothing but irrotational flow. Now, to understand irrotational flow, let us consider a flowing fluid. Now, this is a flowing fluid. And let us consider a mass of fluid. So I have considered a certain mass of fluid, and this is the center of mass. I have marked the center of mass. Now, for the flow to be irrotational, the mass of the fluid should not be rotating about its center of mass. Therefore, irrotational flow can be defined as follows. Actually, it is a flow in which there is no rotation of the mass of the fluid about its center of mass. The fluid only moves ahead in one direction, and there is no rotation of the fluid, of a certain mass of fluid, about its center of mass. So no rotation of fluid mass about its COM, that is center of mass. The fluid mass can linearly move ahead, but this rotation is not allowed. The rotation is not allowed. We also define irrotational flow by saying that there should be no turbulence. There should be no turbulence. So whenever turbulence occurs in any fluid flow, the tendency of the fluid to rotate about its center of mass increases. So there should be no turbulence for an irrotational flow. Okay, let's move on to the next two properties, of which the first is the fluid must be non-viscous. Now, what does non-viscous fluid mean? So I've already written the definition. It basically means that there should be no tangential forces between neighboring layers of the fluid. Let us understand this graphically. So let's say I have two layers shown by the red color. One is the top layer and another is the bottom layer. Now the top layer has slided a little bit ahead and the bottom layer has remained behind. So what happens is the top layer is pulled backwards by the bottom layer and the bottom layer is pulled forwards by the top layer. Now these are the tangential forces of friction that act between two layers, two neighboring layers of the fluid. So since there is a relative velocity between the two layers of the fluid, one layer is sliding ahead and another remains behind. To avoid this relative sliding, the forces of internal friction act between the layers of the fluid, and the top layer is pulled backwards and the bottom layer is pulled forwards to avoid the slipping. When we consider non-viscous fluid, we say that these tangential forces of internal friction are zero. So we neglect them, we discard them. We do not consider the tangential forces of friction in non-viscous fluid. So these forces over here, these blue colored forces over here, we discard the internal friction forces between neighboring layers. Neighboring layers. We do not consider these forces. So that is how we define a non-viscous fluid. Now the last property is nothing but the flow must be steady. So for fluid to be an ideal fluid, its flow must be steady. Now what is the meaning of a steady flow? I've already written it. It means basically that the velocity of the flow at any point does not change with time. Now, what does this actually mean? Let's say I have a pipe like this, which is tapering towards the right end. I have 3 points. Point 1, point 2, and point 3. 1, 2, and 3. The velocity at point 1 is v1. The velocity at point 2 is v2. And the velocity at point 3 is v3. And they all are different. So at different points in space, the velocity is different. But an important point for steady flow that we must remember is that even though the velocities at different points are different, all the velocities do not change with time. Do not change with time. All the velocities do not change with time, which means that v1 is constant, v2 is constant, and v3 is also constant. So a steady flow means a flow in which velocity at different points can be different, but all the velocities at those different points are constant in time. They do not change with time. So these are all the four properties that must be satisfied for a fluid to be called as an ideal fluid. So let's quickly summarize the properties of the ideal fluid. First, the fluid must be compressible, which means that the density should be constant. Second, the flow must be irrotational, which means there should be no turbulence. Third, the fluid must be non-viscous, which means there should be no tangential forces. No tangential forces between layers. And fourth, the flow must be steady, which means velocity at all points must be constant. Velocity at all points must be constant. Okay. So let's move on to the next topic in this chapter, which is nothing but pressure. Now here we are talking about the pressure exerted by the fluid. Now where does the fluid exert pressure? A certain mass of fluid exerts a pressure on its neighboring mass. Then the fluid can also exert the pressure on the walls of the container, as shown in the figure on the left hand side, and also on the bottom of the container. Now over here, we are concerned with the pressure exerted by the fluid on the walls and the surface of the container. So let us define first the pressure. So it is defined as a normal force exerted by fluid at rest per unit surface area. So basically pressure is nothing but perpendicular force exerted by the fluid on a unit area. It is a scalar quantity. The unit of force is Newton and the unit of area is meter square. Therefore, the unit of pressure is Newton per meter square. And this Newton per meter square is also called as Pascal. And the symbol for Pascal is capital P, small a, PA. This is the SI unit of the system. There is another unit also that we use to measure huge values of pressure, and it is called as bar. So 1 bar of pressure is nothing but 10 to power 5 Pascal. So that's all about pressure. The only thing that you need to remember is this formula. Pressure is perpendicular force over area, and its SI unit is Pascal. And there is one more unit called as bar, where 1 bar of pressure is nothing but 10 to power 5 pascals. Okay. Let's quickly move on to the next topic, which is nothing but pressure exerted by a liquid column. So for that, on the left-hand side of the screen, you can see a figure where I've shown a vessel. And in that vessel, I've considered a cylindrical column made up of the liquid. And we have to find out the pressure exerted by this cylindrical column of liquid on the base area A, which I've shaded. So for that, let's have a look at some notations first. The density of the liquid is taken as rho. The area of the cylinder's cross section is capital A, which I have shaded. Then the height of the cylinder, because of whom we are going to calculate the pressure, is h. And the mass of the liquid inside the cylinder is m. So let's first have a look at the weight of the liquid column, which is exerting a downward force on the shaded area. So we can write that weight as W is equal to mg, where m is nothing but the mass of the liquid inside the cylinder. This force is perpendicular. The weight acts like this, vertically downwards. So the force of weight, which is mg, is perpendicular to the base area, and therefore the pressure on the bottom surface of the cylinder can be written as P is equal to weight upon area, which is nothing but mg upon area. Mg upon area. Now let's simplify this mg upon area and try to get the formula for pressure exerted by the liquid column. Okay, so this was the last relation that we got. Pressure is equal to mg upon area. Now, let's simplify this. We know mass is nothing but density times volume. Density times volume. Now, if we substitute this in the place of mass, the equation of pressure becomes rho Vg upon area. And we know that volume can be written as area times height, where h is nothing but the height of the cylinder of the liquid, which is exerting the pressure on the bottom area A. Divided by A and A gets cancelled. And so we have the pressure exerted by the liquid column as rho Gh. So we can clearly see that if the height of the cylindrical column increases, then the pressure exerted by the cylindrical column of water also increases. Now from this formula, we can write down the factors on which pressure exerted by liquid column depends. So let's write it down. So pressure exerted by liquid column depends on first density of liquid, then it depends on gravitational acceleration, and third, it depends on height of the liquid column. Okay. So thus we have seen that the pressure exerted by a liquid column of height h on the bottom surface is nothing but P is equal to rho G h. Okay. So based on the formula that we just derived, P is equal to rho G h, which is pressure exerted by a liquid column on the base. Let's solve a question. So in this question, they have given a tapering vessel where the area at the top is 10 to the power minus 3 meter square. The area at the bottom is 2 into 10 to the power minus 3 meter square. The density of the liquid is given as 900 kg per meter cube, and the height of the vessel is 0.4 meter, which is completely filled with the liquid. What we have to find out is the force acting on the base of the vessel, and we have to consider G, the value 10. So to calculate force, let's first calculate pressure. So pressure is rho GH, where rho is 900, G is 10, and H is 0.4. So you can do it. 900 and 10 times 0.4 is 4. 4 nines are 36. So it is 3600 Pascal. 3600 Pascal. Now, we know pressure is force over area. So to find out the force, we just multiply pressure and area. So pressure is 3600 and area is 2 into 10 to the power minus 3. So 10 to the power minus 3 into 3600 gives me 3.6 into 2, and 3.6 times 2 is 7.2 Newton. So the answer, I think, is 7.2 newtons. Okay, so let's wind up the first lecture over here. See you again in the next lecture of mechanical properties of fluids. Thank you very much.